it's Matthew. Today we're going to learn the common ion effect.
Hello everyone. Today let's talk about subtleties of KSP calculations and the common ion effect. There are some subtleties that can arise when calculating with solubility. Also, we'll introduce the famous, well, I mentioned it already, the famous common ion effect. Alright, so first of all, let's look at a situation with a pre-existing solution, and we want to make some predictions about what will happen. So consider a 12-liter sample of 0.1 molar ammonium sulfide solution. What, if anything, will happen if solid iron 2 nitrate is added? So we need to think about iron 2 nitrate, and as it turns out, it's soluble, very soluble actually, and iron 2 nitrate dissociates like this, making the iron 2 plus ion and these nitrate ions. Notice that the iron 2 sulfide is not very soluble, however. And so we expect a precipitate of iron sulfide to form. Look at that, 6.0 by 10 to the minus 19 KSP. Iron 2 sulfide is a very low KSP value and not that soluble. So anyway, we expect this iron 2 sulfide precipitate to form. And once it forms, the sulfate or the iron 2 sulfide precipitate should do this solubility equilibrium we see here. So that precipitate will fall down to the bottom and, as I mentioned, establish the solubility equilibrium that you can see in the reaction. So I guess the real question that we want to get to comes next here, and that is what mass of iron nitrate can we add to the solution before the precipitate forms? So to solve this, we need the solubility equilibrium and KSP expressions for the precipitate that we're concerned about, and that's the iron 2 sulfide here in the solubility expression with the KSP from above. And also we need the KSP value, which would be the iron ion concentration by the sulfide ion concentration, and multiply them together. So there's 12 liters of this stuff. Remember, it's 0.1 molar ammonium sulfide. And the question is, what mass of iron 2 nitrate can we drop into here before precipitate forms? The KSP we know, the iron 2 ion, we're going to try and determine its concentration, and the sulfide ion, that's pre-existing in the solution. So let's determine what its concentration is. Remember, the solution is 0.1 molar. Here's the ammonium sulfide dissociating, makes 2 ammonium ions and the sulfide ion. So they're 1 to 2 to 1 mole ratio here, 1 to 2 to 1. And this concentration will be 0.1 molar, that'll be 0.2 and 0.1 molar again. So that's pre-existing at 0.1 molar. Anyway, let's solve for the iron ion concentration now. It's the KSP divided by the sulfide ion concentration. Values are now shown, and we get 6.0 by 10 to the minus 18 molar for the iron ion concentration. So it's really only a tiny concentration of iron 2 plus ions that can exist in the solution before beginning to precipitate with the sulfide ions. Let's determine now the mass of iron 2 nitrate that can be added before that precipitation takes place. So here's how to do it. We start with our unit analysis. It's 12 liters of solution. We know the concentration of the iron ion from above is 6.0 by 10 to the minus 18 molar. And here we have 1 iron 2 plus ion for every 1 iron nitrate formula unit that dissociates. You will get the molar mass of iron nitrate as 179.9 grams. Compute all this and get, after checking the units, they all come out good, as 1.3 by 10 to minus 14 grams of iron nitrate before the precipitate is formed. That's not very much. In fact, it's really worth noticing that for any practical purpose, this vanishingly small mass is effectively zero. Okay, so the important insight here is to take notice of the different concentrations. In our case, the sulfide ion was pre-existing in the solution. So just make sure that you don't have the idea that the ions are coming from the solid. In this case, it wasn't. Now let's look at the famous common ion effect. So here we have the common ion effect. And the idea is well illustrated by this example. Here are 2 half-liter samples of distilled water and sodium chloride at 0.1 molar. And the question is, into which container can more lead 2 chloride be dissolved? And the common ion effect actually reduces the solubility of any compound containing an ion that is in common with the pre-existing solution. That makes sense. I think you would expect that you could put less lead chloride into the solution that had the chloride ion in it already. Well, here's the solubility equilibrium expression for the lead 2 chloride with its KSP. And on the left, we'll calculate here for the distilled water. So we'll just write the KSP expression and get the chloride ion here as twice the lead 2 plus ion concentration, and that'll also be twice the lead 2 chloride ion concentration. So here's the KSP expression, just a quick solution on this one. We wind up that the KSP is 4 times the lead chloride concentration cubed. Anyway, compute that here, compute the lead chloride concentration as the cube root of KSP over 4, and it winds up as 0.0144 molar. And consequently, we just multiply here half a liter, 0.0144 mole per liter, and the molar mass of lead 2 chloride is 278.1 gram per mole. Turns out 2 grams of lead chloride will dissolve in the first solution. Now let's do the second one, same KSP expression, and here we have the lead chloride doing its dissociation. We're going to need an ice table now. So there's no lead to start off with, but the chloride ion was at 0.1 molar. The reaction will go to the right as X and 2X in the change line. Fill out the ice table as shown. Let's use our graphing calculators now. We'll plug in for Y1 here, the expression of KSP, the value, and for Y2, the actual algebraic expression. Setting up a window and solving this guy here with an intersect, we get 0.0011. So consequently, the 0.0011 is 1.15 by 10 to the minus 3 molar, yeah? So there's the lead 2 chloride as 1.15 by 10 to the minus 3 molar. Same calculation as before, half a liter, now 0.0015 mole per liter, and 270.1 gram per mole. Calculate, and we get 0.197 grams of lead 2 chloride. Clearly, significantly less lead 2 chloride was dissolvable in the solution that had the chloride ion in it already. Okay, so clearly less soluble in sodium chloride than in distilled water. That's the common ion effect. The solubility should be reduced if there's an ion in common. Also, be careful with this x less than or much less than argument. It does lead to less complex calculations, but it doesn't work all the time. So let me just suggest here, if we had made that approximation, we had the KSP is equal to x times the chloride ion concentration squared, like 2x was less than equal to this guy, or x equal, or is equal to, x times 0.1 squared, and solve this, we would wind up with, just doing all the calculations here, it'd wind up with 0.0168 grams, and that 0.168 grams is not 0.197 grams we got before. So the approximate method doesn't always give you the same value as the non-approximate method, and I would warn you to be careful. So there it is, that's the common ion effect anyway, working, reducing the solubility. Have a look at the next 2 videos for more, and stay tuned for our next lesson in Chemistry 12, Lesson 16, an Introduction to Acids and Bases.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!